Now that we've established these four types of patterns, we can use them to determine what kind of function we're working with if we're given a table of function values. So here's an example. We have a table of values and we want to identify the pattern and the kind of function that has this pattern. So the four patterns that we have established are add, multiply, multiply, and finally the constant second difference. See if you can remember which function applies to which pattern. All right, add is a linear function. Add multiply is exponential. Multiply is a power function. And finally, the constant second difference is a quadratic. So let's see if we can determine if any of these patterns apply to this table of function values. First of all, if it's add, then we would determine how much are we adding to x to get our next value in the table. So here, it's pretty obvious, we are adding 1. Now we'll see if we can determine a consistent y pattern through addition. To get from 5 to 7, we'd add 2. To get from 7 to 11, we'd add 4. So we're not adding the same value for y when we add the same value for x. Therefore, add, and linear don't apply to this example. Let's try another pattern. Add, multiply. Okay, well, actually, I could have left the ones over here on the left. Now, to get from 5 to 7, I would have to multiply by 7 over 5. If I multiply 5 by 7 over 5, I get 7. To get from 7 to 11, I would have to multiply by 11 over 7. We can see right there that there is no consistent pattern of multiplication to get from one y value to the next if we're looking at an addition pattern for my x values. So that eliminates the add, multiply, or exponential opportunity. So let's look at multiply. If I try to establish a multiplication pattern for my x's, let's see. If I multiply 4 by 2, I would end up at 8. But if I multiply 5 by 2, I end up at 10. And 10 isn't a value in our table of values. So we can't actually test for the multiply, or power function. In this case, there's just not enough data, or not the right data, to test for multiply. So by process of elimination, it should be the constant second difference if this applies to any of the four functions that we looked at. But let's test just to make sure. So we do have that regular consistent change in x on this side. I changed from 5 to 7 by adding 2, 7 to 11 by adding 4, 11 to 17 by adding 6, and 17 to 25 by adding 8. Now my second difference I got from 2 to 4 by adding 2, 4 to 6 by adding 2, and 6 to 8 by adding 2. I do have a constant second difference. So that constant second difference tells me I'm working with a quadratic function. Here's another way we can apply the information that we've gained by establishing these patterns. if I'm given two data points and I know what type of function I'm working with, I can predict or establish new data points. For instance, if I have these points f of 5 equals 12 and f of 10 equals 18, so I have the 2 points 5, 12 and 10, 18 for x and y, and I know that I'm working with a linear function, then I know that my data points will have an add-add pattern. So I just need to determine the specific add-add pattern that applies to these data points. Well, I can see that when I add 5 here, then I add 6 here. Now, if I continue to apply that pattern, I can establish new data points. So if I add another 5, I'll end up at 15, and over here I would add 6, so I would end up at 24. If I repeat that process and add 5 again, I end up at 20, and if I add 6, I'll end up at 30. So if f is a linear function, f of 20 is 30. Let's take a look at if f is a power function. Well, in that case, my 2 points, 5, 12, and 10, 18, need to fall within a multiply-multiply pattern. So I ask myself, what did I have to multiply 5 by to get to my next value, 10? So that was times 2. What do I need to multiply 12 by to get to my value, 18? So times 18 over 12, which is equal to 3/2. If I continue my pattern here, I go from 10 to 20 by multiplying by 2. So my next value for y, I would have to multiply by the same value I did before, or 3/2, and 3/2 of 18 is 27. So f of 20 for a power function will be 27. Finally, let's take a look at the exponential situation. So we set up our table again, 5, 12, and 10, 18 for my x's and y's. And now I use the exponential pattern, which is add, multiply. So here I'm adding 5, and here I'm multiplying by 3/2. So if I add 5 again, I at 15. And if I multiply by 3/2, I end up with 27. Now I need to add 5 again to get 20, and I need to multiply 27 by 3/2. That's a tough one. Half of 27 is 13.5. So if I add 13.5 to 27, I get 40.5. So if those data points are part of an exponential function, f of 20 will be 40.5. Notice I didn't have to, in any of these cases, determine what the actual function was. I simply knew that the pattern would appear for that type of function, and I could apply it to the information I already had.